At MIT, I work on language processing broadly. And what I want to talk about today specifically is models for language generation, machine learning models for language generation, and ways in which they sort of do and do not actually accurately learn to represent the meaning of language in the course of learning to generate it. And most of the work that I'm going to be talking about today is by Belinda Lee and Max Nye, who are both students here. Okay, so I want to start with some motivation. I guess I forgot to put the citation on this slide, but the sort of background for this talk is that in the last really just like 3 years, the extent to which machine learning models just trained on big text corpora can generate text that's at least like superficially sort of coherent and fluent, stays on topic, has increased enormously. So here's an example from a model that was trained by a group called OpenAI in San Francisco. You prompt this model. So a human writes, this initial text that's in bold. In a shocking finding, scientists discovered a herd of unicorns living in a previously unexplored valley in the Andes Mountains. They speak English. And then you ask the model to generate the next couple of paragraphs in this article. And a predictive model of text that's just been trained on sort of documents that were scraped from the internet in a particular way completes this passage by saying the scientists named the population after the distinctive horn of its unicorn. I'm not going to read the whole thing, but it basically, talks in a meaningful way with some oddities about a population of English-speaking unicorns living in a valley in the Andes, and generates a bunch of other sort of plausible descriptions of the process by which such a population of unicorns might have come to be found. Here's another example of actually the same model trained to do language generation. And sorry, I'm realizing I can't see all of my slides, so I'm gonna try to minimize the Zoom thing. Okay. Sorry, hopefully that'll be a little easier to see. Here's another passage. The passage reads as follows. Janet and Penny went to the store to get presents for Jack. Janet said, "I will buy Jack a top." "Don't get Jack a top," said Penny. "He has a top, he will ... And we ask the same predictive model of text to complete this passage here. And it says, "He will get a top, I will get Jack a top," says Janet. Now, in this example that we were looking at previously, but even in the example that we were looking at on this slide, there are a couple of things that are sort of remarkable to note here. One is that this model is actually getting a lot of things right? It sort of knows who the participants in this conversation are. It knows that there's an individual named Jack. It knows that there's an individual named Janet that were mentioned really like at the beginning of this paragraph here. It knows that the topic of conversation here is whether we should get Jack a top or not. It knows enough about the sort of like structure of discourses and the structure of conversations to know that it's Janet who's likely to speak next here. And these are all things that, again, I think as recently as like 4 years ago, I think we did not expect was going to be possible with just like big machine learning models trained to do this kind of next word prediction task. But the other important thing to notice about this particular passage is that it's total nonsense, right? That, we say, don't get Jack a top, he has a top, he will get a top, I will get him a top. So this is not actually a sequence of sentences that you could actually imagine, any sort of set of sane human speakers producing on the subject of getting Jack a top. And so the whole field is in this sort of wonderful in-between state right now, where we have these models for language generation that are capable of doing really impressive stuff that looks like this, but that also fail and sort of fall down in these really embarrassing ways. And so we're trying to simultaneously understand what is it that they're actually learning about the structure of language, in virtue of which they're able to get things like the high-level structure of this discourse right, but also what are they getting wrong, and what are the things that we need to do in order to fix them. And in particular, if we look at this passage, we can tell that, thinking about the sort of levels of representation of language at which there might be problems, we're generating coherent words. Our models of sort of English orthography are great. We're in fact generating syntactically well-formed sentence. Our models of syntax are pretty good. And where these models are really falling down, or where there's some amount of uncertainty about what it is that they're doing right or wrong, has to do with representations of meaning. And so what we're really going to be trying to understand in today's talk is the extent to which these models can, in principle, or are already learning something about meaning, and to the extent that they are, what those meaning representations that are being learned just from this text generation task look like, and how we might tap into them in order to actually fix all of these failure modes that we were seeing before. Okay, so in order to do this, let's start by being just like a little bit more specific about the kinds of models that we're looking at right now. The details are not actually going to matter that much, and I'm not going to go in great depth into how these models work, but they roughly look like this. If I'm given a prefix of a sentence that looks like this: John has a book, Mary has an apple, he gave her his, and we're trying to predict the word that's coming next. The way we're going to do that prediction is as follows. We're first going to assign every word in this sentence some kind of vector embedding. We're going to, sort of map every word to some like high dimensional point in some high dimensional vector space. And then we're going to perform a sequence of computational steps that look like this. The representation of every word in the sentence is going to look at the representation of every other word in the sentence at the same layer, and it's going to compute some sort of update that gives it a new representation that now incorporates information about all of the other words that are in the sentence, right? So if I have, I'm sitting on top of the word book might say, well, let me look at the representation of the word John and update my own representation of book to reflect the fact that, I'm a book possessed by John, or that there's, more generically an individual named John in the sentence. And we're going to repeat this process several times, where the representation of every word sort of updates itself by looking at the representations of all of the other words that we computed on the previous round. And what we'll get out at the end of this is a sequence, again, of these just like word representations that now capture information about the context in which that word occurs in this sentence. And so we've only drawn sort of 3 of these vectors here, but in every layer here, we have 1 of these vectors for every word in the sentence. And once we get to the end of this process, to this final layer, we'll take the representation of the final word in the sentence, and we'll just do something that looks like a logistic regression to try to get from that word representation onto a distribution over all of the words in the vocabulary that might come next. And in this case, we want this model, for example, to be able to predict book because it's John that possesses the book and not Mary. Okay, so these are the kinds of models that we're going to be working with. And, again, if you sort of make these vector spaces large enough and you make the computations that transform these vectors big enough, just by training models that look like this, you can do this kind of text generation. The other thing that we need to know, if we're going to try to understand the extent to which these sort of models are actually able to model the meaning of these sentences in order to do these generation tasks, is to be a little bit more formal about what we mean by meaning. And so here's a sort of sketch of what it might look like to represent the meaning of this passage that we were looking at before. So if we have the sentence, Janet went to the store to get Jack a top, we're going to imagine that that sentence sort of calls into existence some sort of structured description of the current state of the world that we can represent as a graph, and the graph might look a little bit like this, right? So we have in this world, there's a store, there's Janet, there's Jack, there's the top, and there's some sort of getting event that relates all of these things to each other, right? Janet is the one doing the getting event, Jack is the beneficiary of the getting event, the top is the theme, and so on. For the sort of actual semanticists in the audience, we're going to play really fast and loose with the sort of actual formal details of these things. But at a high level, think of the state of the world as represented by a graph whose nodes are entities and whose edges are the relations between those entities or events. Okay, and the important thing about this there's a couple of things that are important about the sketch here. One is that, inherent in this graph that we've drawn is information both about what we know about the state of the world and also what we don't know about the state of the world, right? So for example, this top that Janet is trying to get for Jack. We don't know any of the details about the top. We don't know its color. We don't know its relation to other entities in this world. It might be the case that Jack already possesses, in fact, the top that Janet was trying to go to the store to get, and so on and so forth. And so we're going to think of one of these graphs as really representing our information about the current state of the world, both what we know and what we are still uncertain about. And I'm going to refer to these sometimes as information states for exactly this reason. The other important thing about this picture is that as we generate more sentences, right, as we're building up one of these kinds of discourses like we saw before, we're going to think of each new sentence as specifying an update to this graph structure that we had. So if I start with a sentence, Janet went to the store to get Jack a top, and then I add, Jack already has a colorful top. I'm going to think of what this sentence does as extending the graph by introducing a new edge, creating a new top entity, right? A different top from the one that Janet was already trying to buy, noting that the top is colorful and that Jack already possesses the top. And another important thing about the way we're going to think about these kinds of graph structures is we're going to think of them as implicitly including edges, not just for those entities and relations and events that are specifically mentioned by this discourse, but also for those things that are sort of logically necessary consequences of the discourse that we've seen so far. So if we say instead as our second sentence, she gave it to him, we're going to think of our representation of the state of the world as now containing an edge just between Jack and a top, reflecting the fact that Jack has the top. And this is going to be the case, even though we haven't actually said, sort of explicitly in textual form anywhere that Jack possesses the top. We only know, or we only have text saying she gave it to him. Okay, so here's our sort of high-level sketch of how we're going to think about what meanings look like for purposes of today's talk. And I'll note again for the linguists in the audience that this is in fact a sketch that comes from sort of deep places in the linguistics literature under a family of approaches to semantics that are broadly referred to as dynamic semantics. There are differences between these theories. The differences are not going to be relevant for our purposes today. And really at a high level, we're just going to think of meanings in the context of discourses as graphs of sort of entities and properties and relations that are incrementally built up by the sentences that constitute a discourse. Okay, so why is this sketch, or why might these kinds of meaning representations be relevant to this language generation task that we're trying to tackle? And hopefully it's relatively intuitive that if we had access to these kinds of explicit structured representation of the state of the world, then this problem of figuring out what sentence might come next in this discourse, the problem of generating coherent language, becomes a lot easier, right? That if I want to know whether it's plausible to say Jack will get a top, it's much easier to do that if I can sort of look at some explicit representation of the state of the world and test whether Jack already has the top. And in fact, or rather specifically in computational terms, will be easier to do that by looking at some explicit meaning representation than by trying to model relations between surface forms, right? Than trying to model the relationship between the string Jack will get a top and the string Jack has a colorful top. And so we might hope that in the course of learning to generate text, machine learning models come up with some kind of theory of meaning that looks sort of like this, and that it might be something that we can hook into to understand how it is that they're working. Now, of course, we saw this picture before, and we saw that they can't literally be producing these kinds of structured graph-like representations because there's nowhere fundamentally for them to put those kinds of representations in these models that we've been looking at, right? That, sort of the models that we saw before, going, I guess now all the way several slides back, just involve like stacks of contextual representations of individual words. And one consequence of that is that, you can't sort of literally write a graph into one of these models. And so the question that we want to ask instead is whether these kinds of meaning representations, right, these kinds of graph structures are somehow implicitly encoded in those vector representations that these models actually know how to communicate or how to construct. And if so, whether we can actually recover those implicit representations of meanings from the computations and the representations being produced by these models. Okay, so how are we going to do this? Here's now another picture, and we're going to use a slightly different set of example sentences. Suppose we start with the following story. You see a locked door, you are holding its key. And one of these models that we looked at before, as we saw, is first going to encode that sentence in a sequence of vectors, and then is going to decode it to a sequence of words at the output. And we can correspondingly represent this situation that's described by the first two sentences in the following way, right? We have the entity you, we have the entity the key, we have the entity the door. What we basically want to do is try to look at the representation that this model produces, right? The representation that lives between the encoder in this model and the decoder in this model, and to try to understand, whether some implicit representation of this graph actually lives there. this is a sort of structured object, and so we're going to need to come up with some relatively complicated procedure for doing so, and that at a high level, the procedure is going to look something like the following. We're going to try to read this graph structure off, like one edge, or roughly speaking, one logical proposition at a time, right? So the door is locked. We want to sort of specifically look at the fact the door is locked and see if we can extract the truth or falsehood of the statement the door is locked from the representations being computed in this model using what we're going to call a probe, right? So something that's going to sort of reach into the guts of this model and try to figure out, given a proposition like the door is locked, whether that is true, whether that is definitely false, given all the information that we know in our current information state, or whether the truth or falsity of this proposition is unknown. There are a couple of different things that we're going to need to actually implement this probing approach. The first is that we need some way of taking this proposition, like the door is locked, and encoding it, roughly speaking, in the same language that the model itself already speaks, right? So we have, on one hand, a bunch of vector representations of text. On the other hand, we have this structured proposition of a structured proposition saying the door is locked, and we want to figure out how to relate these things to each other. And so we're going to do this by taking this proposition, the door is locked, and embedding it in the same vector space that the model already uses, actually using the same encoding scheme produced by the model itself. Right, so I'm going to take this sort of logical proposition or this graph fragment. I'm going to, in just some rule-based way, translate it into a natural language sentence, and then I'm going to hand that sentence off to the same encoding machinery that the model itself uses when trying to predict the word that's going to come next in a sentence. And that's going to give me a vector representation of this logical proposition. Now that I have this, the next thing that I need to do is figure out where in all of the representations produced by this model, information about the truth or falsity of this proposition might be recorded. And to do this, we're going to introduce another tool that we call a localizer, which is going to look at one of these propositions that we're trying to ask a question about, like whether the door is locked. And it's going to extract from this model the representation of a specific word or sequence of words that we think might be candidates for encoding the information about the proposition that we're trying to understand, right? So in this context, where the door is locked, we're going to look at the word door. For other propositions, we might look at other words, and we'll actually look in some detail later on at how we can use this tool to get a relatively fine-grained understanding of where information lives in these models. But roughly speaking, given one of these propositions, we're going to try to decode information about those propositions from mentions of the entities that are involved in the propositions in the text. And then the last thing that we need is something that can actually look at our representation of a proposition like the door is locked, look at our representation of the word door produced by this model, and actually map this to a sort of true, false, unknown value in the context of one of these discourses. And this we're going to do with a sort of single linear model. So we're going to start with a big training corpus, right, of sentences where we've actually gone in and annotated by hand these kinds of structured meaning representations, annotated by hand the truth or falsity or unknownness of individual propositions. And we're going to train basically a linear regression model to map from our proposition representations and our token representations produced by the models to these truth or falsehood values. And we're going to see if these things generalize. And the important thing to notice about this piece of the model, or this step of our decoding process, is that this sort of matrix involved in this linear regression step is the only free parameter in this model, right? So the sort of actual encodings, or is the only free parameter in the probe. So the actual encodings produced by our model for the language generation task, we're trained only to do this language generation task without any explicit representations of meaning. The process by which we encode these propositions uses that same machinery, which was trained without any explicit representations of meaning. And so all we're using to actually look for these meaning representations inside these models is a single matrix, right? A single sort of linear regression step that's going to try to relate the propositions to text. And that means that in particular, if we can do this reliably, and if we can generalize to sort of new documents and new propositions and new contexts, that will mean that the information that we're looking for, these kinds of meaning representations understood as atomic logical propositions, are already linearly encoded in the representations produced by these machine learning models themselves. Okay, and yeah, so again, concretely, we'll start with some text data sets. We'll go in and hand annotate a bunch of these logical forms. We will not use these logical forms or graph representations or whatever to train these models. We'll use them only to train a single weight matrix in this probe, and we'll see if we can actually then use this probe to understand something about whether and how these models are actually representing meaning. To do this experimentally, we're going to be looking at two different text data sets. The first of them is called alchemy, and in alchemy we get sort of sequences of sentences describing, like elementary laboratory bench procedures where you have a sort of beakers full of colored liquids, and you see instructions that tell you to pour some beakers into other beakers or mix beakers or whatever. And when we think about the kinds of things that we need to understand about the state of the world in order to just do well at generation, at this alchemy task, you really do need to understand the states of all of these beakers, right? It doesn't make sense to talk about mixing a beaker that only contains fluid that has one color, or a beaker that has no fluid in it at all. We similarly can't talk about emptying out beakers that have no liquid in them, or adding liquid to beakers that are already full to the top. And so we expect that in order to do well at this alchemy task and to sort of know or be able to just generate coherent text without actually looking at sort of explicit representations of the state of the world, we nonetheless need to implicitly track the state in which every one of these beakers might be. And it happens that we can use this not just as a text generation data set, but that we have access to two ground truth annotations for the state of the world that we're going to use to set up this probing procedure that we saw before. The other set of experiments we're going to be looking at involve an environment called Text World, which is a text adventure game. So, for those of you who are old enough to have ever played any of these before the real age of graphical video games or whatever, you imagine a scenario where you're sort of sitting at a terminal, something prints out, you're navigating through a house, you've entered a study, there's a mantle in the room, blah, blah, blah. You're given some sort of task and you want to interact with these text adventure games by typing in commands that you might follow here by, saying in this room, for example, like go east or open the toolbox, and so on and so forth. And so similarly, we're going to be training our language generation model just to generate sort of plausible looking playthroughs of these games. So we're going to get transcripts of people playing the game. We'll train a model to sort of generate other transcripts. And similarly, in order for these things to be semantically coherent, it's going to need to be the case that these models only interact with objects that we've already seen, that they interact with them in plausible ways, that they remember their states, right? That whether a door is opened or closed or locked, whether a chest contains any objects, or whether we've already removed all of the objects from the chest. Yeah, and I guess maybe even to put this in slightly more explicit kind of linguistic terms, the main thing that we're going to be looking at in this alchemy data set has to do with anaphora, right? That there's a lot of, sort of both explicit and implicit references to entities that you've mentioned before and figuring out their states and so on and so forth. And in text world, I guess there's less sort of specifically on the linguistic side, and that it instead has to do mostly with modeling objects, modeling affordances of objects, and sort of really keeping track in a fine-grained way of your state in a large and open-ended environment. Okay, and having introduced these data sets, we can just go straight to what happens when we try to train one of these semantic probes to recover the underlying state of the world from the representations of text produced by these models. And the main thing that we observe is that you can actually do this with quite high accuracy. So in this alchemy environment, right, we train our probe as we saw before, and then we evaluate on new documents reflecting new initial states and new final states of the environment. And we find that even in those new documents, we can exactly recover the state of 75% of beakers. And this is true for a couple of different variations of these text generation models, the details of which are not actually all that important, other than it really doesn't seem to be all that important how you train the model. You can still, just by learning to generate text in this alchemy world, produce representations of that text from which you can recover the underlying state of individual beakers. And this is even more true in the text adventure game, where you can actually get 96% of entity states exactly right? So every logical proposition that we have describing that entity exactly right when we train this probing model and evaluate it in new environments. Just to put these two numbers in context, if we assume that no object ever changes its state, basically such that if we just look at its initial mention and everything that is included in the initial mention of that object, we get 62% and 74% accuracy on both of these tasks. And if we just assume that objects are in their most frequent states in the discourse, without really looking at the text at all, you get 32% and 81%. So these baselines are quite high, especially in this text world data set. But the important thing to notice is that we're doing substantially better than them, and in kind of an absolute sense, exactly recovering the underlying state of most objects mentioned in these documents. Another thing that we can try to do is understand aspects of the training procedure that contribute to this behavior. And one important thing that we didn't really talk about at the beginning of this talk is that all of those really impressive text generation results, right? The English-speaking unicorns, whatever, you get them by training truly enormous models on truly enormous amounts of data, like to first order the entire internet and learning to predict the next word from every sentence that you scraped from the internet. In the experiments that we've been looking at here, we also have lots of little sort of domain-specific data, right? We have a big corpus of documents that are just these, sort of alchemy, like mixing beakers together documents, or just playthroughs of these text adventure games. And so one other question that we can ask is, do we learn more about meaning by training on a sort of big open domain corpus that looks like the internet, or by training on really specific and in particular domain-specific corpora describing just these laboratory protocols or just these games? And one surprising thing is that it turns out, from the perspective of doing well at these probing tasks, but not necessarily language generation tasks, that the really important thing is training on a really huge open-ended data set. So if you train, start out by training on the entire internet and then fine-tune the parameters of your model a little bit on one of these tasks, that gives you the best performance. But you lose only a tiny, tiny bit of accuracy at this probing task if you just train on the entire internet and you don't actually fine-tune your text generation model for the task at hand at all. So most of these models' ability to track, the states of beakers, or whether chests are open or whether doors are unlocked, is actually learned from open domain text rather than these domain-specific things. And conversely, if we only train on the domain-specific data, you do better than these baselines, but not all that well in an absolute sense. And maybe the most interesting thing is that this sort of procedure that we developed before gives us fine-grained tools for understanding not just that this information is encoded by these models, but where this information is encoded by these models. And to sort of figure out how we might do this, let's think back to that localizer piece of our probe before, right? So we said before we were going to have some sort of black box piece of this probe that would look at the proposition that we were trying to classify, pick some piece of the text, to extract the relevant information from, and then hand it off to our linear regression model. Let's now look at the implications of constructing that localizer in a couple of different ways. So suppose we have in this alchemy world a document that begins in the following way. The third beaker has 4 units of blue, the fourth beaker has 4 something, something, something. And then at the end of this document, we have the sentence, empty beaker 3. If we point our probe just at the word has, just in the initial mention of this third beaker, we can recover, or I guess generically, if when we're trying to understand the final state of beaker n, we point our probe at the main verb in the sentence that introduces beaker n, we can on average recover the final state of that beaker with 64% accuracy. And if we sort of abstract this over all of the beakers in our document and all of the positions in the sentences mentioning those beakers to begin with, we find that most of the information about the final state of that beaker is included in its initial mention of the beaker in the document, right? That if we look at has, we look at for, we look at blue, we can get the final state quite accurately, even though the final state is that the beaker is empty. And conversely, if we look elsewhere in the sentence, or particularly if we look at initial mentions of other entities elsewhere in the document, we do much worse at these kinds of tasks. And what the sort of picture that this sort of paints of the computation that goes on in these models is then something like the following. When an entity is mentioned in a discourse, we're going to construct we're going to use basically the vectors that live above the mention of that entity as a repository of all of the information that we know about the state of that entity at the end of the discourse. And as we append sentences to this discourse that change the state of the entity, we're going to reach back to the entity representation that we built above its initial mention and update those vector representations of the entity to reflect its new state at the end of the discourse. And so in particular, right, when we mention a locked wooden door and then we unlock the door, the final representation of the word locked is going to reflect the fact that the sort of lockedness state no longer holds. And one cool thing about this picture is that it is literally a picture from one of these dynamic semantics papers that we mentioned at the beginning of the talk, right? So, sort of linguistic theories about how we might represent meanings in discourses turn out, at least in some approximate way, to actually get reified in these big machine learning models that are just trained to do next word prediction without any explicit information about semantics or what semantic representations might look like. Now, one final question that we can ask here, okay, these representations are getting built up, but are they actually being used by the model in the way that we might expect them to influence downstream generation? Basically, is it just the case that we're winding up with representations that are like correlated with the final states of entities, or do these actually participate in some causal fashion in downstream model behavior? And to answer this question, we're going to do one final experiment, which is going to work as follows. We're going to set up two different discourses that describe the same initial state of the world, but different final states of the world, right? So in one, we're going to say the first beaker has 2 green, the second beaker has 2 red, the third beaker has 1 green, and we're going to drain 2 from the first beaker. In the second, we're going to set up the same initial state of the world, but we're going to drain 2 from the second beaker. And so we wind up with these information states at the end that look different in these two cases. And we expect correspondingly that the initial description of the world will be different across these two sentences. We're now going to do the following. We're going to construct a sort of Franken representation here that doesn't correspond to any actual text that we could hand to the model. And we're going to do that by taking our context number 1 that we drew in blue, in which the first beaker winds up empty. And we're going to remove the representation of the second beaker that was produced by that model. And we're going to replace it with the representation of the second beaker that was produced by the model that we handed this other context, in which the final state of the second beaker was that the second beaker was empty. And so sort of implicitly what we've done is we've built a vector representation of the state of the world in which both the first beaker is empty and the second beaker is empty. And this is not something, right, that was directly encoded by any model, but that we sort of built by hand by stitching together different pieces of entity representations that we took from totally different documents. If we now take this Franken representation that we produced and we hand it off to the decoder, the model that's going to try to predict the next sentence that might come in this document, given everything that came before, we find that, in fact, it preferentially generates instructions to empty the third beaker and not to generate sentences that involve stirring the red beaker, right, which would be allowed in the original version of context 1, or to stir the first beaker or the green beaker, which would be allowed in initial mentions of context 2. And that in particular, if we look at the fraction of generations produced by the decoder in this new mixed context, 80% of those are consistent with the mixed context, and a much smaller fraction of those are consistent with either of the two states that we saw before. And so what this tells us is that this sort of picture of ways in which models are representing the state of the world actually turns out also to be a picture that's used for decoding, and that we can build these world states from scratch and predict how they are going to affect downstream model generation. So to sort of start to wrap up here, there's a couple of different pieces of the story. This is still like, the main paper was published at ACL. This is very much work in progress. And one thing that we're really interested in understanding is what the relationship is between this picture and failures of generation, like the failures of generation that we saw at the very beginning of the talk. And so one thing that you can do is plot in a bunch of different contexts that you saw, the probability that a random sample from this language model is actually semantically acceptable versus the probability that a randomly sampled fact is correctly classified as true, false, or unknown. And if you do this, these things are basically uncorrelated with each other. And what this tells us is that as much as when the model is sort of doing the right thing, it's doing so by looking at these underlying representations, we can't directly attribute errors in generation to errors in construction of the underlying world state. And one sort of hypothesis that we have about what's going on here is that sometimes this generation problem is still very hard, and sometimes also this encoding problem is very hard. And so the model is not always going to produce fully accurate underlying world states. And so if I'm the decoder, right, and I'm handed some sort of world state, and I'm told basically this is like, there's a 90% chance that any individual piece of this world state that I is actually accurately represented. As a probabilistic model of sentences that might come next in this document, it's going to be really important for me to put probability mass on sentences that are not actually consistent with this underlying world state, because when that state is wrong, I still want to be able to assign probability to sentences that might come next in the document that contradict the underlying world state. And so trying to figure out, what exactly is going on here, and in particular, how we might better couple language generation to these states, so that it happens, 100% of the time and not just most of the time, is one interesting research question. And another, super pressing question from the perspective of actually understanding what's already going on inside these models, is to extend this story to much more complicated semantic phenomena. So we sort of pointed to the dynamic semantics literature at the beginning of this talk. Most of what that formal framework was designed to do, at least in a sort of linguistic context, was to deal with really messy problems involving quantification. We have said nothing at all about quantification today. All of the experiments that we were looking at involve no interesting quantification of any kind. In fact, there's just one of every entity in each of these discourses. And so figuring out what this sort of representational story that we've told looks like once you deal with part-whole relations and with aggregates and with sets containing multiple entities, and even more complicated logical phenomena like implication and counterfactuals, is again a super interesting question that we're hoping to look at soon, but that we don't know anything about yet now. And finally, with my sort of engineer hat on and just interested in building better models for language generation, the natural question is whether we can use these same tools now, not just to understand what's going on inside the models that we have, but to make those models better. And one very natural way to do this is to say, okay, well, now that I know what the model is trying to do, and now that I know how these language generation models are sort of trying to come up with a representation of the underlying state of the world, can I actually make those better by just telling the model how it should be representing the world? And one way we can do this is now by taking this probe, this thing that we used at the end of the training procedure, after we'd already trained our model and frozen its parameters, and actually sort of throwing it in at training time, and saying to the model, as you're doing next word prediction, it should also be the case that if I point the probe at the representations that you're producing of individual entities, those representations are actually correct. And obviously this sort of explicit data about the representation of information states is quite precious. We're never going to have access to the same amounts of it as we have access to just raw text data for training these text generation models. But we have some very preliminary results suggesting that on sort of standard measures of language generation performance, if you train these models to produce accurate semantic representations while you are also training them to produce text, the quality of the generated text actually gets better. And one even more sort of extreme thing that you can do is say, okay, this story that, at the end of the day, this model that we've described, or the initial model that we've been looking at today, is still trying to model basically just relations between linguistic forms and linguistic forms, right? It's looking at all of the text in the context. It's trying to predict some text next. Maybe it produces some explicit underlying state of the world, or some sort of implicit representation of one of these semantic graphs as a byproduct of that procedure, but it's not sort of fundamental to the computation. And there's no point at which you are actually explicitly conditioning on something that is just a semantic representation of the state of the world. And as we suggested at the beginning of the talk, that is something that we might actually expect to make this generation process easier than just trying to model the relation between sentences and sentences. And so one thing that you can do is say to this model, don't now just learn a mapping from strings to strings, but explicitly learn a mapping from strings to these underlying world states and from underlying world states to the strings that are going to come next. And if you do this, again, you can get some little gains from doing this. And the cool thing is that you can do this in a very weakly supervised way, where you start with a data set of many, many sentences, only a small fraction of which you've annotated with these sort of rich semantic annotations. At training time, you can use information about what text is coming next to help you impute these semantic representations for all of your other training data. And then you can use those imputed semantic representations to do better at the downstream text generation task as well. Good, and I think I will actually wrap up there. So just to sort of summarize what we saw today, language models, right? Machine learning models trained to do just like next word prediction or next sentence prediction, given text as input, implicitly encode in their latent representations, semantic representations of the underlying state of the world. And we saw that these semantic representations of the world that they build, that you can learn from text alone, are actually highly structured, right? They localize information about individual entities and individual propositions in sort of understandable ways. And more than that, they can actually be manipulated in structured ways with predictable effects on downstream language generation. At the same time, we saw that both these language generation models and these implicit meaning representations that they produce are far from 100% reliable, and we saw sort of ended with lots of open questions about what exactly is going on in these things and how we might both improve them explicitly, sort of in their own right, and as a stepping stone towards better downstream language generation. And I'll end there. So thank you very much.
Thank you so much.